Okay, so now we're continuing the absorption problem, and we are calculating the number of stages now. Before we go ahead and see what we're gonna do here, I just want to quickly revise how we calculate the number of stages. So it's gonna be very much like what we did in the McCabe-Thiele diagram when we calculated the number of stages. Here we have the and this looks like yeah, the same. We have the operating line and the equilibrium curve, and we calculate the stages by drawing a line starting from here, going down, and then it intersects with the equilibrium curve, and then goes to the left until it intersects with the operating line, and so on, stage by stage, until we reach the final concentration that we have here, or the y at this point. Once we exceed this point, we're done. So what we need to do now is to um, uh, keep in mind that this is a vertical line that has a constant x, and the second point satisfies the equilibrium curve equation, and that's why we extracted or did the fitting to get the equation of the equilibrium curve. And the same here, this has constant y line, and it intersects here. One other thing that we will be interested in is to calculate the fraction of the stage. So I'm gonna zoom in to this part of the curve, so or the diagram. So we have this. This is what we are doing. So to get the fraction of the stage, we are gonna stop at this point. And to calculate the fraction, what we need to do is to, or it's based on our understanding that we need this part of the stage, and this is the extra part. So I need this fraction of the stage. To calculate this fraction, we need to define x1 and x2, and these are points that I'm gonna be calculating already, so I'm not gonna calculate something new. These numbers are already gonna be calculated when before I do the or draw the stage. And the part that I'm interested in is the part I call M, and the whole stage is represented by n. So the fraction is m divided by n, which is going to be xb minus x1, or divided by x2 minus x1. You can do the same using this part and this part. It's going to be almost the same, so it's not going to make a big difference, or they're going to be small difference between them, but both will work. So this is how we calculate the fraction, and I kind of am interested in making sure that you understand this part, because it's kind of confusing when we go into the calculations. It might be a little confusing, so I hope it's clear now. So now what I need to do is to start uh, the calculation of the number of stages. So they just to have kind of understanding of the relation between the operating line and the column. This point here is xa and ya, which is corresponds to this part of the column, and this is xb and yb, which corresponds to this part. So it's the opposite shape of the column. The top part of the operating line is the lowest part of the column, and the bottom part of the operating line is the maximum point on the column. So I want to start by drawing a line starting from xb and yb, I mean xa and ya, and going down. So each line is represented by two points. So the first point is xa and ya, which is this and this, and this is a constant x line, so the x is known. And now I want to calculate the y that has this value of x and satisfies the equilibrium curve equation. So I'm going to substitute in this equation using the value of x. So it's going to be 2.7838 multiplied by x power 2 plus 0.6599 multiplied by x plus 0.0008. So this is the first line. I am just to confirm that this doesn't have any issues. Let's make it a little bigger, and I'm gonna select data. Again, it's one nice thing that you can do is to name the lines well, so that you don't have, or that you don't get confused when you deal with it. So this is the line. Again, we need to make sure that it has solid line. So it's great. It's doing what I want to do. Now the second point, or the second line, is gonna start from the end of the first line. So x is gonna be this, and y is gonna be this, and this is a constant y line, so the y is constant, and this is a line that will intersect with the operating line and satisfy the equation of the operating line, which is y equals ax plus b, or x equals y minus intercept divided by the slope. I can do the same and select data, add a line which is stage 1b. The x data are these and the y data are these, and that's it, and it has a solid line. So I'm now done with the first stage, and the rest is gonna be very similar, but I need to do something first, which is put F4 or click F4 here and here, so that when I copy and paste, I don't lose the locations of the cells. This is gonna start from where the last point ended, or the last line ended, and the rest is gonna be just copy and paste. So this is what I'm doing now. I can copy this and paste as many times as I want. So I want to stop at the point where I reach the value of xb equals 0. So this is the goal now. I'm doing the calculations. Still x is 0.018. I'm getting it's now 0.007, so I'm getting close, and now it's almost 0. So it seems that I need only 6 stages, but actually this is not exactly 0. This is we can make it scientific. It's something multiplied by 10 to the minus 4. So this is not exactly the value. So it seems that I need to use 6 stages and a little fraction. You can draw the rest of the lines here, but for the sake of time, I'm not gonna do the same thing because it's just repeating the same thing. But I have already done that here. And from here you see that these are the lines. I have 1, 2, 3, 4, 5, 6. It looks like 6, but it's not actually 6. And this is the number that I mentioned before. It is something very small number. So I need now to calculate the number of stages in a more accurate way using the equation that I mentioned here. So I now know that I have 6 stages, and the fraction would be in the 7th stage. And from my understanding of the shape of the curve, or the stages, and the understanding of the numbers here, it seemed that these stages didn't do a lot of things. So it just achieved 0.000 something change in the concentration, or in the mole ratio. So I understand that this is a very small portion of the stage. So what I'm gonna do is to calculate the equation based on this equation. It's xb minus x1. This is xb. I'm gonna put f4 here for a reason that I mention in few seconds. Minus x1 divided by x2 minus x1. So that's it. No, I think I did a mistake. It's xb. Oh, I'm sorry. It's minus x1. This is x1, and this is x2 minus x1. So it's 0.02. So this is what I expect from the numbers that I have. So the number of theoretical stages is going to be 1, 2, 3, 4, 5, 6.02. And this might be everything, and I can be done after doing this. But I want to go a step further and make it calculate the number of stages manually or automatically without having any doing anything from myself. And the reason I'm doing this is because you can, for some reason, change the flow rate. And in this case, you'd see that I have 1, 2, 3, 4, 5, 6, 7, 8 or 7 point something, and this fraction that I have here shouldn't be here now, it should be here. So I now have 7.86. So by doing any changes to the feed flow rates or the compositions of the feed, I'll have a corresponding change in the number of stages, and I don't want to do this manually. So what I'm gonna do is something that's kind of simple, but it's kind of smart as well. I'm gonna calculate the fraction for all the stages, and that's why I used or clicked on F4 when I wrote this formula, so that the XB is placed as constant. So I'm gonna do this for all of them, and I'm gonna take a look at them just to kind of understand how the numbers go. So I know that I have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 stages and a fraction. So for these 7 stages here, I can see that the fraction of the stage is a number that's greater than 1. And for the stage that has a fraction, it's a fraction between 0 and 1, and the rest are negative values. So I will write an if conditional here, and I'm going to tell it if this number is greater than 1, consider this as a stage and put a value of 1, and else if this is smaller than 0, so this is not a stage, so put 0, so you cannot consider this as a stage. Otherwise, keep it because it's going to be a fraction. So this is simply what I did. I'm going to repeat this for all the stages so that I can oops, I'm sorry. So what I did is I copied and pasted the same formula for all of them, and from this I can calculate the sum of all the stages now. So if I calculate this sum, it's gonna give me exactly the number of stages that I need to achieve this separation. And now for any change in the inputs, I will see the corresponding number of stages. So let's say I'm making this now 1.4. So it's giving me the number as 4.53 without having to recalculate the fraction for the stage or do any manual calculations to know how many actual stages or full stages and how many or what's the fraction of the rest of the stage. If for instance I change it to 0.15, sorry, 0.15, I will have it 5 point something, and it's all the stages are drawn and the number of stages are calculated, so I don't have to worry about anything or do anything manually anymore. So I'm gonna bring it back to the original value, and finally I need to calculate the actual number of stages if the efficiency is 25%. So it's simply the number of theoretical stages divided by the efficiency, which is 24 point something. But this number has to be a whole number, and in this case, if it's 24 point something, I'm gonna use 25 because you have to approximate it to the larger integer. So the function that does this is called ceiling, and this is the number, and I'm gonna put 1, so it goes to the following integer. If I put 2, it's gonna be 2 integers and so on. So now it's 24 point something, and then now it's giving as 25. So again, by changing anything now, if I use point 0 or point 12, the number of theoretical and actual stages and the graph are all updated automatically. So the system will work, or this file will work for any change in the inputs, and all the outputs are going to be calculated automatically. So I hope you like it, and I'll see you in the next video, inshallah. We're going to do the stripping, which is the opposite process. So I'll see you then, inshallah. Goodbye.